Yeah, so I'm going to talk about Copenhagen Atomics, a Copenhagen startup company, and thorium energy. So a lump that size made out of thorium, you can hold it in your hand, it's the size of a golf ball. It can provide you with all the energy you need for your entire life. Not just electricity, but everything. You mean your share of hospitals and houses and roads and all the products you use throughout your entire life. It's quite amazing you can get all that energy out of this small ball. And the cost of a ball like that, when it's mined out of the ground, is roughly $100. So if you live for 100 years, it's like $1 per year for the raw material to produce all the green energy you would need for your entire life. That is a big opportunity, and this is what Copenhagen Atomics is working on, developing that technology. Of course, after you have the thorium out of the ground, you still need a machine that can convert that metal into energy, and this is what we develop. And actually, Copenhagen Atomics is leading the world development in this thorium energy. So it's quite exciting that we're developing this right here in Copenhagen, and this is what I'm going to talk about today. We believe a lot that energy equals prosperity. So that means, we need a lot of energy in the world if everybody is going to have the same level of prosperity as every one of us here in this room have experienced for our life. There's at least 5 billion people in the world that would really like to have the same level of prosperity as what we experience every day. And that's going to take huge amount of energy, and hopefully green energy. And so this is what we're, again, trying to develop, that energy source that can more than double the amount of energy that we humans build or produce in this world. And I've given many talks of this over the years, hundreds of talks. This one is going to be a little bit technical because, after all, it is the tech stage at Tech Barbecue. So essentially what we want to do is we want to mass manufacture molten salt reactors. And it is a type of nuclear reactor, but it's not like old classical nuclear. It's a different type of nuclear reactor that can convert this thorium into energy. And this is what we're developing right here in Copenhagen. And we want to mass manufacture it on assembly lines where we can make at least one reactor every day. Of course, in the distant future, many reactors every day. And you heard that right. Normally we think about nuclear reactors as something that takes 10 years to build, but we actually want to build one every day on an assembly line. And when we then install it in a nuclear power plant, it looks like this. It looks like a regular distribution center in the outskirts of whatever city you're from, because it's just a building, and inside the building there's an array of reactors, and those reactors are what generates the energy. You need 25 of our reactor units to produce 1 gigawatt of electricity. And this particular building is a project that we're involved in Indonesia. So Copenhagen Atomics wants to build, own, and operate the nuclear power plant. So it's not a government that builds it and operates it. It's Copenhagen Atomics, or one of our subsidiaries in those countries. And we also finance the power plant. So it's a completely different model than the classical model of nuclear energy that we've known for so many years. So what we make is the heat. And we export that heat or sell that heat through molten salts. And then the customer is sort of in the buildings in the background. They will convert that heat into electricity or steam for industrial use. I also show this chart a lot of times because it tells us the history of humans and energy and how that all fits together. When we started back in 1800, or when this chart starts in 1800, we were less than 500 million people on this planet, and now we are 8 billion people. So it really tells you what energy can do. It started sort of the whole industrial revolution. This chart here is, for me, it's like the crankshaft of the international economy. And of course, we have the media and politicians and stuff, and they talk about all kinds of things. For example, every now and then there's some crisis, like the financial crisis in 2008. There's a small bump in the chart. There was the oil crisis in the 70s, another small bump. There was the corona crisis 2020, another small bump. But you see how all the products, all the stuff we need, concrete, steel, aluminium, all that stuff, that takes huge amount of energy. And this chart tells you how that is made and which type of energy sources. And of course, the old energy sources, the fossil fuels, are of course the main driver of this. There's a little bit of classical nuclear, there's a little bit of wind and solar, and those are growing, but not super fast. When you ask sort of the average man on the street here in Europe about, should we build more nuclear, what they will tell you is that it's too expensive, it takes too long time to build, It's very dangerous, and it leaves behind waste that is a big problem. But what if I told you that this is actually not true, or at least we have solutions to solve those problems? Maybe you would reconsider. And what I find when I've spoken to thousands of people is that most people, when they realize that these problems can't be solved, they're really willing to look at nuclear technology and nuclear energy in a new light. And let me go through some of those. So first of all, there's the problem that it's dangerous. Well, that's completely misinformation from the media. Nuclear energy has never been dangerous, and it's still not dangerous. If you look at the international statistics of how many people die from different types of energy sources, you see here that, of course, coal is the most dangerous one. You also see that nuclear energy is on par with wind and solar at the bottom. You also see that these numbers include both accidents in Chernobyl and Fukushima. So these statistics are over many decades. And of course, if those accidents were not included, then it would be, of course, even safer. So it's misinformation that it's dangerous. It has never been dangerous, and it probably never will be. Then there's this thing about radiation. People say, oh, but you remember the Fukushima power plant, it blew up and people had to be evacuated. Well, first of all, it was not a nuclear explosion. It was a hydrogen explosion, and nobody died from that. Of course, it's not supposed to blow up, I agree, but nobody died. Second thing is that people were evacuated, but actually the radiation level in the area where they were evacuated were never at the high level that we have in, for example, Stockholm or Rome. And nobody talks about evacuating all the people in Stockholm or Rome. So it's crazy. It was a big mistake that those people were evacuated, and nobody wants to sort of admit that. But it was not dangerous to stay there, and nobody would have died or even get close to dying if they had stayed. So human error. Now I want to talk a little bit about some of the physics behind nuclear energy. Maybe some of you guys remember this from your high school, maybe not. So all the nuclear energy, or all the nuclear power plants in the world today, they run on what is called uranium-235. It's shown there on the left. And when you hit uranium-235 with a neutron, then you can get it to split. It's called fission. And then you get two fission products, which are the two elements on the right, and then you get some neutrons. And those neutrons are really, really important, because that is what makes it possible to make a chain reaction. And this is why nuclear engineers, they talk about neutron economy all the time when they talk about reactors, because if you don't have the right neutron economy, your reactor's not going to work. And I explain this because I want to explain how it works with thorium, because it's a little bit different with thorium. When you dig thorium out of the ground, it's the one at the bottom here at the chart. So then it's called thorium-232, and you hit that with a neutron, but it won't split. Then it's upgraded to thorium-233. Later it decays to what is called protactinium-233, and then further on to uranium-233. Uranium-233 is an excellent nuclear fuel, and it will fission, and it will generate enough neutrons to have an excellent neutron economy in your reactor. Uranium-233 does not exist in nature, so it's man-made, and it can only be made inside one of these thorium reactors. So that's the difference between classical uranium-based reactors and thorium reactors. But then once it turns into uranium-233, it also fissions in the same way as what was shown in the previous chart. And then if you look at how much thorium do we have on this planet compared to how much of this uranium-235 do we have. So we have at least 1,000 times more thorium, and thorium exists in all countries of this world. So it's very plentiful, and we will never run out of it. And of course, we can generate a lot of green energy from it. So it used to be that classical nuclear energy, based on this thin sliver, the thin orange sliver of uranium-235, was not called renewable, because there was a fear that we would eventually run out of uranium-235. But we're not going to run out of thorium, so thorium is sort of a renewable energy source. Also, if you try to compare thorium to other energy sources that we use today, like oil and gas and coal, if you take 1 kilogram of each one of them and then show how much energy you're getting out of it, you can see that there's some small balls there of the fossil fuels, and then there's a huge ball that doesn't even fit on the slide, which is the thorium. It's so much more energy per kilogram. It's actually more than 1 million times the energy density of the classical fossil fuels. Then there's the argument about the waste. What do we do about the waste from classical nuclear energy, and do we generate waste from the thorium reactors? Well, first of all, let's talk about the waste from classical nuclear reactors. So the symbol up there on the left-hand side is the drum. It represents the waste from classical nuclear reactors. And if you look inside that drum, 95% of that is natural uranium. It's the exact same uranium as was dug out of the ground many years earlier. It hasn't changed at all. The problem is that it's mixed with these last 5%, which is sort of a radioactive and a problem. So if you can separate those two, then you get basically natural uranium, and you could sell that uranium back to the uranium market. But the problem was, in the past, it was not economically viable to make this separation. But it is now, and this is why things are changing in these years. So what we can do with the last 5%, after it has been separated, we can take those last 5%. Those are two things. Those are fission products. Fission products are radioactive, and they need to be stored safe for 300 years and above ground. So not this very expensive deep geological storage, but you can store them above ground for 300 years. And then there's the last part, the orange part there. It's the transuranics and the plutonium. And those are the reason why nuclear waste, usually people say that it needs to be stored for 100,000 years underground. But we can actually take that and use it as a Kickstarter fuel inside thorium reactors. And when we do that, we can generate 10 times more energy out of the material, both the thorium and those transuranics and plutonium, than the amount of energy we got out of the fuel in the first place. So it's sort of an upgrade. It becomes a very, very valuable fuel. And that's also why I believe that in a few years from now, you will see people sort of paying the same as for gold and diamonds for nuclear waste. It's going to be a very, very valuable resource on this planet. Then I want to talk a little bit about the technology that we have developed in Copenhagen Atomics. One of the important things is this special reactor core, which is different than all the other reactors out there in the world. And we have taken patents and trademarks on it. It's called the onion core. And what is so special about this is that it's almost full of heavy water. The blue colors are the heavy water. And the heavy water is there to slow down the neutrons. It's all about this neutron economy to get that to work really well. And then the yellow part around on the outside is the thorium blanket. That is where the neutrons are captured, and that is where we convert the thorium into this uranium-233. And then that uranium-233 is then transferred into those fuel channels in the middle, which are sort of the purple color. And when the fuel gets in the fuel channel, then it's pumped with a pump. It's a liquid salt at 600 degrees. So it comes in at the bottom at 600 degrees, and then at 1 second later, it exits at the top at 700 degrees. And this is when the energy is generated. And then during the time that it flows up through that channel, it generates a huge amount of energy and gives off all these neutrons that are then needed for running the chain reaction. And this is a new type of reactor that we have invented in Copenhagen, and that we are really proud of, because it can really change the price of nuclear energy. I will come back to that a little bit later. Here are some examples of some of the prototypes that we've built. We are not allowed to start a nuclear chain reaction here in Copenhagen at the moment, but what we can do is that we can heat the salt up with electricity and then pump it around and test all the things with flow rates and thermal expansion and all these other things that we need to test. And one of the things we need to test is corrosion. So one of the problems that is a lot of times mentioned on the internet, if you read about molten salt reactors, is the corrosion problem. But we've actually already solved that a couple of years ago. And we're also leading the global development in molten salt technology. And we're selling these salts and this know-how to universities and national labs around the world. So what we do there is in this particular image, you see on the left-hand side, we take some samples and we put them inside this salt at 600 degrees for, in this case, 2,000 hours. And then we look at the corrosion afterwards. And you can see at the lower left-hand picture that you get a lot of corrosion. Actually, the material gets quite damaged if you don't do the purification. But in Copenhagen Atomics, we've developed a process to purify the salt so that we get rid of the corrosion. And then you see on the right-hand side that it almost doesn't change if you run it for 2,000 hours. And we have other tests where we run with different types of salt, different number of hours, different temperatures, and we always get the same results. And this is something that we've been developing for the last 8 years. But we cheated a little bit, because there was actually a group of scientists at the Danish Technical University who have been developing these purification processes for more than 2 decades. So we are standing on the shoulders of giants, and we are really happy that we got to know these guys. And then this is sort of the last free, or the free key selling points of Copenhagen Atomics. So with this new technology, we are able to produce energy at lower cost than any other energy technology. So this is green energy at the lowest energy cost. And we can beat anything from coal or fusion or wind and solar, anything on price. The next thing we bring to the table is a new model for nuclear energy. I mean, nuclear energy throughout all the previous decades, it was something that was, built by governments, owned by governments, regulated by governments, financed by governments. But we bring a new model to the table, one where we as a company and our subsidiaries, we finance, build, own, and operate the power plants. And we believe that is a really important part of being able to provide energy at low cost. And then, of course, finally, the thing that I talked about in the beginning with the waste, we're able to take spent fuel from all the other types of reactors out there and convert that and use that with our thorium reactors and generate 10 times more energy than the other reactors per kilogram. And also, when we leave waste behind, it's the type of waste that only needs to be stored for 300 years above ground. So it still needs storage, but it's a manageable problem. So if we go back and think about that, one of the first slides that I showed, that there's these problems. Okay, so people say that it's too slow and it's too expensive. Well, it's definitely not expensive now. It's actually the cheapest form of energy, and we can build one reactor every day. So those problems are sort of solved. Then there's the danger part. Well, that's a misinformation problem, and our reactors is still going to be one of the safest energy forms in the world in the decades to come. And then finally, of course, there's the waste problem, which I've also shown that we can solve. So this is what Copenhagen Atomics is developing here, right here in Copenhagen. We have a team of 70 people working every day, and we're growing the team month by month. So if you're interested either as an investor or as a potential employee, please come and talk to us because we need all the support we can get to bring this technology to market. Thank you.